How to calculate the whirling speed of a rotating shaft? Let us discuss with the problem. Whirling speed of the shaft is nothing but it is the speed at which resonance occurs in the rotating shaft. So resonance is nothing but it is the condition at which the forced frequency reaches the natural frequency of the system. So this is the problem statement. Calculate the whirling speed of a shaft of 20 mm diameter and 0.6 meter long, carrying 1 kilogram at its midpoint. The density of the shaft material is 40 megagram per meter cube and Young's modulus is 200 giganewton per meter square. Assume the shaft is freely supported. So the given problem can be diagrammatically represented like this. So it is simply supported between its ends. Since the density value is given in the problem, we have to consider the natural frequency of the system due to the self-weight of the shaft too. Okay, and in addition to the self-weight, a 1 kilogram mass is acting at the midpoint of the shaft. So the data given in the problem are: diameter of the shaft small d is 20 millimeter, that is 20 into 10 power minus 3 meter. Length of the shaft small l is 0.6 meter. Magnitude of the centrally acting point load M is equal to 1 kilogram. Therefore, weight of the load, that is W, is equal to 1 into 9.81 Newton. Density of the shaft material rho is given as 40 megagram per meter cube, that is 40 into 10 power 3 kilogram per meter cube. Young's modulus of the shaft material E is given as 200 giganewton per meter square, that is 200 into 10 power 9 Newton per meter square. So it is asked to find the whirling speed of the shaft. So according to the definition of whirling speed, we have to calculate the natural frequency of the system. When the system's forced frequency reaches the natural frequency, then only the system will be rotating with the critical speed, that is whirling speed. Okay, so for that we have to calculate the natural frequency of the system. So for the given transverse vibration condition, we can calculate the natural frequency of the system using Dunkerley's approach. Dunkerley's method suggests the formula to calculate the natural frequency of transverse vibration as Fn is equal to 0.4985 divided by root of del 1 plus del 2 plus del 3 plus up to del n plus del s divided by 1.27. Okay, so here del 1, del 2 and del 3 are the deflection experienced by the shaft or beam due to the point loads. Okay, and del s is the deflection experienced by the shaft due to the self weight. Okay, so here in the considered problem there is only one point load which is located at the midpoint of the shaft, and since density value is given in the problem, we have to consider the effect of self-weight also in the calculation of natural frequency. So we can simplify this formula for the present case as del 1 plus del s by 1.27. Okay, so first we can consider the point load which is acting exactly at the center point of the shaft. The given shaft is simply supported between its ends, so we can calculate the deflection experienced by the shaft due to the centrally acting point load. The formula is WL cube divided by 48 EI. Okay, weight value is 1 into 9.81 Newton, so 9.81 into length of the shaft, total length of the shaft is 0.6 cube divided by 48 into Young's modulus value is 200 into 10 power 9 Newton per meter square. Moment of inertia value we have to calculate. So since the cross section of the shaft is circular, we can calculate the moment of inertia I using the formula pi by 64 d power 4. Okay, so pi by 64 into diameter d is 20 into 10 power minus 3 meter. So we can get the value of moment of inertia of the shaft as 7.854 into 10 power minus 9 meter power 4. 7.854 into 10 power minus 9. Okay. So we can get the value of del 1 as 2.8104 into 10 power minus 5 meter. Next we can calculate the deflection experienced by the shaft due to the self weight. So density value of the shaft is given as 40 megagram per meter cube, that is 40 into 10 power 3 kilogram per meter cube. Okay. So using the density value we can calculate the mass of the shaft using the formula rho into A into L. Okay. So rho into circular area as pi by 4 d square into length of the shaft. Okay. So the density value is 40 into 10 power 3. Diameter is 20 into 10 power minus 3 meter into length of the shaft is 0.6 meter. Okay. So on calculating this we can get the value of mass of the given shaft as 7.5398 kilogram. Okay. Here weight value should be considered for the calculation of deflection. So weight can be obtained by multiplying the mass value by 9.81. So the weight of the shaft is 73.9654 Newton. So deflection experienced by the shaft due to the self weight in case of simply supported beam, the formula is del S is equal to 5 by 384 into WL power 4 by EI. Okay. So here W is the value of the UDL. Okay. So it should be substituted in the unit of Newton per meter. The unit for UDL is Newton per meter, that is weight per unit length. So in the previous step we have calculated the value of weight of the shaft, but here we have to substitute the value of W, that is weight per unit length. So total weight of the shaft is 73.9654 Newton. So which is the weight for 0.6 meter shaft. The given shaft is having 0.6 meter length. So for 1 meter if we calculate, we can get the value of W in terms of Newton per meter. So the UDL value is 123.2757 Newton per meter. Okay. So now we can substitute the UDL value here to calculate the del S. 123.2757 into length of the shaft is 0.6 meter divided by Young's modulus is 200 into 10 power 9 into I value as 7.854 into 10 power minus 9. So the del S value can be obtained as 1.3243 into 10 power minus 4 meter. Okay. So now we have calculated the deflection experienced by the shaft due to the point load as well as the self weight of the shaft. So now we can substitute del 1 and del S value in the natural frequency formula. 0.4985 divided by root of del 1 is 2.8104 into 10 power minus 5 meter plus del S is 1.3243 into 10 power minus 4 divided by 1.27. So by calculating this, we can get the value of natural frequency of the given system as 43.3266 Hz. Okay. So in the problem, it is asked to calculate the whirling speed of the shaft. Frequency is nothing but cycles per unit time. Okay. So we can write this F1 as 43.3266 cycles per unit time, or we can represent this as revolution per second. Okay. When the shaft's frequency reaches this natural frequency value, then the shaft will be rotating with the critical speed. Okay. So the critical speed NC will be 43.3266 revolution per second. In terms of revolution per minute, which is 2599.596 RPM. Okay.